Hello everyone, welcome back to the session. Today we will start to learn about boundary condition effect. Still we are covering the column and part 2, local strengths. Let's get it. So the aim of this lecture, we will try to understand what is the elastic buckling for various boundary conditions, and that is actually keyword. So don't forget. So elastic buckling, and one more thing is the boundary condition. That's all. So here we will have a look what kind of boundary conditions we have, and we will try to formulate we will try to drive all the formulations to get critical buckling load and derivation. I've mentioned effective length concept, and finally, we could be able to design our structure members to avoid the buckling using the relevant formulations. So last class at the end, I have introduced briefly about effective length. And here, let us remind it again. So basically, we have 4 exactly same columns as you could see here. And then exactly same amount of the force axial compression P is applied for all columns here. But one thing, of course, the all material properties, length, apply the force, everything is same conditions, but only one boundary condition different. So as you can see here, the first one, this is for the simply supported boundary condition, like pin-pin condition, and this is for the one fixed here, and the other part is free. This is fixed, this is fixed, this is fixed, and this is simply supported or pinned. So 4 conditions, and then once we apply the axial compression, the deflection shape, everything has been represented by dotted line, red color. So important thing is here actually, what I want to highlight is this one, this one, this one, and this one. So please think about it. What was the meaning of the effective length for this case? And basically what we have learned before is proposed by the Euler, elastic buckling force, which can be calculated by pi square EI over length square. And actually this L should be converted to LE, which means that effective length should be placed here. But please, this LE is L original length times K. These can be defined by here. So in this case, K is 1.0 for simply supported condition. This case, this boundary condition K value is 2.0. K is 0.5. K is 0.7. So it is pretty much simpler. We can just simplify it and then substitute it here. So this effective length will be changed, scale, and then finally we can get elastic buckling force. You know what I'm saying? So again, the meaning of effective length is effectively whole length will be utilized for simply supported case. But in this case, 2L, which means that another 1L is required to cover this condition. In this case, only half. It should be like that. half length 0.5L will be used to cover this, first. And then in this case, here to here, the length will be 0.7. That is effective length concept. Okay. So we've seen this video again only for 1 minute. You can see now the boundary condition, the difference, and then deflection shape, amount of the load carrying capacity, boundary condition effect, as well as effective length. In this case, whole length has been used, so effective length is 1, meaning that pin-pin condition. So this is pin and, if I'm not mistaken, fixed condition. So that effective length here, as you can see here, it looks like 0.7. We've seen it from the previous slide here. It's like that. Now you can understand what I'm talking about, right? So again, we learned about the Euler Formula 250 years ago, simply supported conditions. It was like that. And then the length can be, converted based on the assumed boundary condition, like effective length concept. But here now we will try to drive it mathematical expressions. So apply the compression is P. This is actual compression. Same amount will be applied at here P. And then this is reaction P here. And once we apply the actual compression, of course, this beam will be deflected like this or that, but we will just assume it like this way. And then we're gonna have this much of the deflection W. So just assume that this is X and cut the section, bring it, this green color is our column, apply the actual force is P, and then because we cut the section, we will experience the shear as well as moment. So this is moment, this is shear, this is certain length. So based on this, how to establish the equations. So this can be considered as free body diagram. Based on this, we can establish P, apply the first P times W. This is moment, right? Plus moment value should be balanced. This is equation number 1. And we learned this relationship from the simple beam theory before. That is, what is this? Bending stiffness and deflection 2 times. So we can simply substitute it here and simplify it so that we can get these equations. So next slide, you can predict that how we're gonna, solve these mathematical problems. So we will remind about the ODE. I do believe that you have learned it from mathematical courses. So we are here. The governing equation is already given like that. And then don't be confused. So we will assume that alpha square will be apply the first actual force P over EI. So divide it 1 over EI here, so that this will be EI here, same. So this part will be assumed as alpha square, and this part is still the same. So now we are here, alpha, and how are we gonna get to find the function W? W is actually deflection, and the deflection along the length of the column that can be represented by Wx. So we want to know the deflection function along the length of the beam or column. So in this case, we can assume that this equation can be utilized to find the function. 2 unknowns, constraint, and the next step will be we need to think about boundary conditions. because we have to determine those two unknowns A and B, right? So in the case of simply supported case, so the solution, second order, linear, homogeneous, ordinary differential equations, so we call the ODE. I do believe that you have learned this before from the mathematical courses. So now what we have is this equation, and then this is exactly same as this equation. And here, how to get this? So I do suggest you to check this link if you forgot how to get this. And then basically it is not difficult. W assume it like this way, and then set the boundary condition, and then substitute all the conditions. So two unknowns, two boundary conditions used, and then we can determine A and B so that we can finalize these deflection functions. So detailed procedures are here. So what we have is this function now, and then in the case of boundary condition, think about it, this is simply supported case. So let's say this is A and this is B, and at A what we have is deflection should be 0. At B deflection should be 0. Can you understand? At the same time, the moment should also be 0. Moment should also be 0. What I'm talking about is, again, simply supported and clamped or fixed. Deflection, slope, and moment. In this case, simply supported case, at both edge, that should be 0. Clamped condition 0. Slope, finite and 0. In the case of moment, 0. And yeah, this one I just brought it to here. Now you can understand what I'm talking about. So what we have is deflection function here, wx, and when x equal to 0, this means A. X equal to L is also 0 at B. So we can decide B as well as A. So after this, you can see that we have obtained these equations at L. So in order to meet these criteria to be 0, then the A should be 0, first condition, and the second condition is sine alpha L should also be 0 as well. So in this case, no buckling occurred, and in order to meet these conditions, we can think about the shape of the sine functions is like that. This is fx equal to sine x. So this is sine alpha L. So here, in order to meet 0, then here, there, and there. So that should be pi, 2 pi, 3 pi, something like that. Now you can understand it. So based on this, we can simplify further, and then you can get these equations. Alpha square was P over EI, and bring it all the obtained outcome here, right? So from this procedure, we have obtained these Euler buckling formulations, and this has been derived based on buckling mode shape. So what was the advantage of this sine function? So basically, the deflection will be assumed like buckling mode, like wave shape. So of course, in reality, the shape of the buckling, it should not be like perfectly like buckling mode. Sometimes the shape will be like this is perfectly like that, but sometimes it's like this, or sometimes like that. It really depends. But the advantage of this buckling mode is it is simple and clear. Sine function 2 times then it will become moment. It will be sine. See the sine, because one time is sine, it will be changed to cosine. One more time, sine. So all the time, the scientists, engineers, they do prefer to adopt the sine function. What I'm talking about is buckling mode shape. So in this case, you can see here the mode 1, the global mode shape. Mode 2 means, mode 2, where is it? Mode 2 is here in red color, up one time and down one time. So this is mode 2, up and down. Mode 3 should be up, down, up. 4 is up, down, up, down. So it is like that. This is buckling mode shape. Can be represented by this one, and N we called half wave number. You know what I'm saying? Based on this N value, this shape, mode 1, 2, 3, 4 can be decided. So the procedure is, let's have a look. So cut the beam column at a distance x from the spot at left, run it, and we can sketch the free body diagram, and equilibrium should be applied, and established governing equations, moment curvature relationship should be substituted to this governing equation so that we can solve it. So after that, what we need is boundary conditions, right? So after that, we can solve all the details, buckling load and mode, and then we can select, this is important, the minimum buckling load as a critical. What I'm talking about is here, before this slide, we've seen this, like mode n equal to 1, 2, 3, 4, 5, 10, but choose lowest value of p, which means that n equal to 1 will be selected as minimum. That should be considered as critical one. So that was important for us. And then let us try to generalize it, because if we generalize it, what I mean is, look at this boundary condition. This is a fixed condition or the clamped condition. Because simply supported boundary condition, we don't experience any type of moment. So in this fixed conditions, we initially have moment like that. So it can be considered as well. And initially we have the reaction force here as a shape of shear R. So that can also be considered as well. So moment equilibrium, moment, that equations are shown in here. Apply the moment is same as initial moment, and reaction force times distance x, and apply the force P times deflection W. So based on these, from the simple beam theory, we can bring this again. That is exactly same as M, and then this part is rewrite here, and then simplify it again. So nothing special. What we had done is just consider here initial moment and the reaction force, so that the equation can be simplified again. So what will be the next? Think about the boundary conditions, and then in order to get the general solutions to solve this ODE. So in this case, this shape of the deflection function can be selected to decide A, B, C, D, 4 unknowns, which means that we need 4 boundary conditions. So that's for sure. And please remind this one again. Simple beam theory, we learn it many times, and that's why I have highlighted from the marine mechanics part. So pin or the simply supported case, deflection 0, at the same time moment is also 0, fixed condition, deflection 0, and the slope, this is exactly the same as slope, is also 0. Free condition is like our ship conditions from front and the end. So the moment should be 0, because in this case, why they are not talking about deflection and slope is because it is free. We have nothing. We cannot get any information from here if we talk about free condition. That's why we have to see moment first, 0, and then shear, that is also 0. So each have 2 conditions. Therefore, we can find 4 unknowns now, A, B, C, D, right? So based on this, we can move on. So solutions for all possible cases. Based on that, we can substitute all the boundary conditions so that we can decide all those important equations, and then we can extract the coefficient like k values, in this case 1, 2, 0.5, and 0.7, and that values k represent the effective length is like that. Now you are familiar with this, right? So this is the exactly same information again. So once we have this equation, frankly speaking, we can do everything. So based on the boundary condition, we can calculate this elastic buckling force, and this shows the coefficient representing the effective length. And based on this, we can see that, oh, this L, the K value will be varying. So fixed condition, you should understand the physical meaning now about the coefficient. So effectively, 0.5 times L, only half of the length of the column will be utilized to cover that the actual compression. That is reason why you can see here this is 0.5 L square, so it will perform like 4 times better than simply supported case. This is k equal to 1. So even we use the exactly same material, same length, based on the boundary condition, we can make big major changes of the structural capacity subjected to the actual compression. This is my main point from this lecture, topic 11, the importance of the boundary condition. So that is the judgment by our engineers. So let's move on. So if we have initial deflection, initial imperfection, as you could see here, due to the welding, fabrication, induced distortion, of course, our column could be initially, deflected. Why not? From the transportation, from the manufacturing, fabrication, from the welding, we can experience the distortions like that or here. So how to consider this kind of realistic issues? So in particular, buckling capacity of shell structures are very sensitive to initial imperfections. And imperfection sensitivity of column can be checked mathematically. As you can see here, this is our assumed column here, initial imperfection, initial deflection. We will now think that initially our column is deflected. As you can see here, still we are using sine function, the buckling shape. We call it buckling shape, like sine function has been adopted, assumed to be having initial deflection, like that's why they put note here, W note. This means initial deflection of the column. So this amount this is actually amplitude if we have the sine function f(x) equal to a sine x. This a represent the height or the amplitude of the sine function. So in this case, this is initial deflection amount. So this is exactly the same as here, amplitude, and this is function. So the total deflection total will be Wx plus W naught is initial deflection, and due to the compression, this one will be developed. So final that can be obtained like that. So now you can understand what I'm talking about. The other procedure exactly same. So here, based on that, we can solve governing equations, and we can assume the conditions here based on the boundary conditions. We can solve it so that we can finally obtain this one nearly, that is magnification factor. So based on this amount of the initial deflection or initial imperfection, so it can be reduced like this factor based, right? So previously our column, important, our column was like that, and then now our column is slightly deflected, like this amount deflected, but in this case no deflection, perfect column, ideal condition. So this is number one, this is number two. Number one is represented by red dot, and number two is here. You might be understand what I'm talking about. So once we apply the load to our perfectly straight column, then even we apply the load from the beginning to certain amount, it will maintain the straight shape, so that you can see here it will be move up till here, then suddenly it will buckled. But in this case, number two, initially we have the deflection. So initial deflection shape, like here, initial deflection amount is this amount, and then it will deformed like that gradually. So that's the main difference. And sketch the perfect and column response on the same graph. You can see here, this is perfect column, and this is initially deflected column. And the reminder, this topic we learned about boundary conditions. That is brilliant information, because even we have the same material, same length, same geometry, based on these boundary condition assumptions, we can change the structural performance. So this is brilliant idea, and now we are able to identify necessary boundary conditions and why and how we select it, and derivation, how to calculate the critical buckling load, effective length concept, and all those details you can find it in lecture note 11. Please have a look. And the next lecture, topic 12, will be collapse strength. We will have a look at the practical, way based on the given design formulations and the shipyard, how they, check the collapse strength, and they do also have the empirical formulations as well. So after topic 12, we will complete the column part, and then we will start about the truss matter by topic 13 to 15. And that's all today. Thank you very much. 감사합니다.